Good afternoon, gentle readers. It's Sunday, May 19, 2024. Well, what I shall so hope to do today is to continue in the discussion and the consideration for moment and motion of meters per second and seconds per meter, or these other notions considering the definition of what is the a study of the theory of the motion with regards to the moments, or what is and isn't motion, in a world where everything is either sort of at motion or with respect to other things, or internally not at motion. That again, like usual, or otherwise previous talks, I suppose, if we're not to make too much for the inductive cases of things, or that the causation and correlation and this kind of thing don't have much about it. But here are some concepts that I've been thinking about and trying to coalesce or to digest with regards to what would seem as apropos. And one of them is about constants, and so I've been studying at some point the roots of phi. So phi is familiar as the golden mean, the golden ratio, and that phi minus 1 equals 1 over phi. And then another thing that I've learned about recently, and only sort of recently, is there's a constant called the lemniscate constant. So if the ratio of the circle's circumference to diameter is pi, constant of the circle, pi, and then whether that's properly 2 pi or pi halves is its own sort of story. That for the lemniscate, which is something like x squared plus y squared, that quantity squared equals x squared minus y squared. Or the lemniscate of Bernoulli, its ratio of its area, or its circumference to its area, is along the lines of this constant called the lemniscate constant. And it's interesting because it's related to something like in an integral form, something like the integral from 0 to 1 of 1 over this quantity, the root of this quantity 1 minus x to the fourth. And so it gets into some of these things like the whole x squared plus minus 1 bit. It gets into things like the integral forms and these other kinds of ideas. And then as with regards to otherwise as a constant, and that it's in the center of these things, so all these limits and completions go to it in a sense. Then as well that it has all its expansions and these ways to write it to, if not in so much the closed forms, but in these infinite expressions, like the integral indicates an infinite expression of sorts, or the forms of series or continued fractions or this or that all these things together come to make it that it's part of this coterie of constants that ends up being relevant to the thing. And if there's another thing I wanted to mention, it was about the parabola and the quadratic. You know, if the parabola is y equals x squared or x equals y squared respectively, then that there's what's called the quadratic sieve, where the idea is there's two concepts at play. And one is that the parabola has a focus, and so that all the rays that fall into the open parabola reflect as of the incidence of their angle and all point at a common focus. And the other one is in the quadratic sieve. This is one of the most remarkable things that I've heard about in mathematics, and I don't know much of having an explanation for it, is that the integer points on the parabola, like 1 and 1, 2 and 4, 3 and 9, and 9 and 81, all the numbers in their perfect squares form these integer points. And so when you connect all the integer points on the parabola so that those on the left would cross the axis to those on the right each. And so as it starts with each one, with 1 to 1 connecting to all the higher points, or vice versa, each point connecting to each of the lower points. So for a case for induction, or that the origin, all the rays are from the origin, you know, both ways, that then this idea that the lines they form cross the axis at either integer or non-integer points, and where they cross the axis at integer points are composite numbers, and where they don't cross the axis at a given integer point is prime numbers. That it sieves, it makes a sieve of the prime numbers. That otherwise the most usual familiar sieve or net, a filter, a way to catch the prime numbers is the sieve of Aristotle's called trial division and brute force and exhaustion to accomplish trial division by each lower prime number until you reach about the square root. So you be sure you've exhausted all of its possible factors. And that the idea that instead there's a simple graphical diagram that just readily connects and indicates, thusly, given the ability to construct a parabola, which is not a classical construction, yet it has a very well understood form and a very singular sort of parametric form, y equals x squared in roots and powers. That the quadratic sieve is one of the greatest things that is worthy of a great amount of explanation to go into explaining how it is that it sieves the prime numbers. And there's one other thing that I thought was just kind of mathematical curiosity. It was about trigonometry. So the other day there was a brief discussion on one of these boards about trigonometry is kind of unfounded, or about how it can be arrived. That basically it was for the Pythagorean theorem and the definition of as from the right triangle and the circular and all that gets into the field of mathematics called trigonometry. So what I was reminded of is that the way that is usually demonstrated and shown that the sine curves, sine and cosine, where sine is familiar since a great period of the ancients, or about 500 AD at least, and then the Muslim Enlightenment really fleshed out sine and cosine and tangent and cotangent and cosine and otherwise the inverses, that secant and cosecant, that the most familiar way that it's drawn out is according to a right triangle is as of about a unit circle. And so I was reminded that kind of like this quadratic sieve is a thing, that the idea of this tri-equilateralometry is a way to make, again, and not as of so much a classical construction, that there is an equilateral triangle instead of a right triangle as kind of its kernel or its form, and you unhinge a side and it unrolls with all the angles opening at the same rate, and out the trace of the unhinged end is also a sine curve. It's the same shape, it's the same curve. As for matters of a scale, then it's to be determined exactly what is the scale of an equilateral triangle with regards to that unit circle, so that then it is the exact same value, these functions of trigonometry, as via quite different means. Because in the discussion it came up, it was like, well, this is how it's done. And it's like, that's not the only way it can be done. So it's changing again what would be a uniqueness result to a distinctness result, and making it so that for both of the ways that one can be built to the other, that then we can get into things like defining, well, can you find the Pythagorean triples, which are the triangles, right triangles with rational sides, make so that you can find a Pythagorean triple. And how can you find right triangles? Well, you find an angle that is right, or you find that it has two angles that sum to a right angle. Either way, if you can find the functions of trigonometry, you can find right triangles, and if you can find right triangles, you can find the functions of trigonometry. And so this kind of converse is just given as an example of something that is not so well explored, but is definitely part of mathematics. It's part of the objects of mathematics, so it exists. So I studied this for a while, in particular, or for 15 minutes, looking around, and there's a great development of it on the Wikipedia, which is always kind of, on the one sense, some of the topics and subjects will become very much kind of moribund and like, this is our dogmatic brief description, picking a very course of opinion that is supposed to say what this kind of thing is, and it's not going to mention or bring in the context or any controversy about it, and it's all just going to be a very much simplified and watered down bit. Whereas so many of the other different particulars in the sections that are dedicated to the specializations, very much so, help fill out the quite fuller and richer detail that then goes into things, so that the things that are so much very general basically must be very free of opinion, where things like is discussed here, that the numbers and the objects in number theory, the objects of arithmetic after increment and division, after a deconstructive account, arithmetic from either side, for parts and wholes, and Mariology, the study of their boundaries and all these kinds of things. For algebra and all these different kinds of algebras, and what happens when it is that the singular points in the algebras become relevant, become openings, perestroikas, catastrophes, or otherwise what are the multiplicities in the singularity theory. The objects of geometry, of course, and how that's very much kind of the center of all these things, because Euclidean geometry is a continuous manifold with an origin, and so that's the Cartesian geometry is very much, kind of like, it's a given of the thing, compared to the entire idea of that, well, in an entirely discontinuous milieu, then at least everything is totally independent and free, which is more for the realm of, the abstraction and such, vis-a-vis that of the concrete. So for number theory, arithmetic, algebra, geometry, and then topology being its own thing, is like how these things come together, because everything comes together somehow out in that discontinuous space. There's all the possible things that it could be. And then with regards to those, and function theory being for matters of relation, has that in logic, the primary elements are often terms. And then there also may be predicates. And then there's also, as for what are relations. And so if terms are basically just symbols or words in a formal language, and then for what the syntax that may be, then there's predicates, which are Boolean or true or false evaluations of a thing, the predicates. And with regards to predicativity and impredicativity, when things don't have only true or false answers, that then there's relations, but relations basically do or don't exist, and then for any two given things, they do or don't relate, and defining kind of what relations are for same and different, and alike and dissimilar, and congruent and incongruent, or then as with regards to equality and tautology and identity for intentionality and extensionality, all these being words for yes or no in relates, and also yes or no in terms of correlates or coincides, approximates, or is proximal, all these things. That then there's the idea that those together make the idea is that each of those are very general, and so each of these are pretty much their own fields. And so in a theory, any one of those could be the primary elementarily fundamental object in the theory, because it's in terms of matters of relation, it kind of boils down to like, pick one of terms, predicates, or relations. Its relations is kind of what is abstract in general, and not one-sided, in the sense. These be axiomatics in terms, and these usual kinds of things that are so regular and rulio, that the very general things have to remain general. And so when something like a curve in geometry is picked out also as a function from function theory according to a usual topology, and then as with regards to modeling with algebras and its operations, and as for arithmetic, of course, and its systems of equalities and systems of inequalities, and all the systems that are used to define rules and regularity and all this kind of stuff, then it's just to be said that all those different things are their own thing, while yet altogether in the same kind of open milieu system, mathematics, the objects of mathematics. So this is a kind of one of those things where then a different kind of subfield, like this differential geometry will say, well, a curve is defined as this and that, and we're going to keep it simple and have no normals or tangents that are 0 or infinity, because then we get a lot of closed forms for free, because the formalization doesn't have to make cases otherwise for them that would fall out. Compared to this singular analysis and integrals was like, well, we just have free analysis, and we're just going to work in these particular cases and kind of build out their particulars, without trying to take over the definition of otherwise the word. That function is probably the object that has seen the most change, and this was kind of brought up several times in this descriptive differential dynamics, that function, the word, is a matter of relation. Is that as the different domains change, then the what are related by among them, the functions change. And when we talk about like even our Cartesian and on paper or graph paper, just drawing charts and diagrams of functions or plots or graphs, and that they used to be called graphing a function, and then it's like, well, now we got graph theory, so we're just going to call it something else. Maybe we call it plotting a function. It's like, well, the plotter is something particular, and then it's two-dimensional, say. Or that, whether to call it a diagram. It's like, well, a diagram is really just when two plots, charts, graphs, or curves drawn on axes or in perspective and projective come together. It just helps to illustrate again that functions are so general that then it's up to each particular subfield to disambiguate for themselves and to establish their own onus, their own burden, their own requirements of keeping that within the well-defined and well-behaved, not on the rest of the field of mathematics, which is like, it's general, and so when you're defining a function, it can be read very generously for what it's to entail between a domain and range, or domain and image, or domain and codomain, as between domains, as it were. That otherwise, that's kind of thing. Well, at the same time, all these different leaves of the fields have all this richness of detail and trail off into all these different expansions. So trying to figure out among those which ones to go together is quite a thing. So another thing that's come up is, and again, this is in a roundabout way, getting around to talking about the meters per second or seconds per meter, and the infinite expressions which result that for walks and runs and stops and pauses, that it's all sort of at once linear and yet original, and it has all the implicits of all the units, while at the same time it's an entire sum of history, sum of potentials for these expressions, was about the convergence and the existence of prototypes in the telescoping and scaffolding of the infinite series that have sensible values. So we talk about the limit today, and it's just to be said that the infinite limit is always associated with a bit of baggage. And so it's associated first for infinite induction, that there exists infinite induction at all. And so in normal modern mathematics, we have Z of set theory, and one of the axioms is the existence of an inductive set, so it's kind of given. And it can be arrived at that deductively it exists, and it can arrive at it inductively it doesn't exist. And so this is just one of those things that's about the very nature of the logical considerations at all, in the logical realm. And then another thing about that is with regards to the infinite expressions, the limit, and the infinite limit. Oh, and the convergence of the series. So different convergences of different kind of series vary according to some very specific kind of given prototypes. And so some of them arise like from the geometric series. And in the Zeno's example, the sum of the infinitely many negative powers of 2 equals 1. This is pretty much the first sort of convergent infinite series that has a limit and an infinite limit, and its limit exists and it's finite. 1. And then other ones begin to arise is from these constants, like from all the infinite roots of phi, or these expressions that are used to build the Fourier analysis after really the great study of the trigonometric functions and their infinite expressions, as with regards to how then Fourier, for example, learned how to put together an expression for any other function in terms of these functions, in terms of the analysis of their signal, in a sense, that for the cases for infinite induction and the infinite limit, is that in mathematics it's already given a very, very central and sort of special milieu because it's in the numbers and they're already unbounded, so there already is a case for induction that infinitely many numbers exist. And so everything in mathematics can be associated with that pretty well, and in fact that's the entire kind of thing for the cases for infinite induction. And then for where things go and the inductive limit is that they do or don't reach or complete, can be said that they can't really complete unless they complete. And so then when we get into things like the almost everywhere, it's like, well, we're assembling countably many regions, a countable area that are measurable, so that we can say we have a sigma algebra and we brought them all together in a sense, and they're measurable, but it's not quite uncountable, so it wouldn't really have a measure. We'll say it's almost everywhere like so, and in fact then after this derivation I'm going to cross out the AE part, almost everywhere, and just say that it's so. It's like, well, you left out a part, in fact you purposely scratched it out, when really there was something there that it was supposed to have been kind of just, so it's like, we need to resolve this in the foundations proper to explain why otherwise this one construction, this other construction, while they attain to each other and build up and down, that they're either complete or they're not. And when then they're not, then when there needs to be established more for the deductive analysis instead of the inductive analysis, why that is so. So that's just a pretty usual thing, but because of the way then the great facility of the common milieu of modern mathematics makes for common formalization and common axiom, has offered so many inroads for axiomatic set theory and descriptive set theory to be a formalization and to provide rigor for all such matters of real analysis that's so necessary, that when in the higher applications it becomes necessary to just kind of skirt around that in the sense of like hedge against it, or like hide or bury it in a sense, then that seems bad, because there's no room for hypocrisy in mathematics, because theoretically it's kind of like the language of computer systems, and if that's undefined behavior, then undefined behavior includes the lights are out and this kind of thing. So that just gets back into the for inductive and deductive inference, that it's kind of deductive inference rules, and but it has to have a place to go. I mean, there's a reason why it gets there for inductive inference to arrive. So finding these very particular prototypes of convergent sequences, and especially the very slowly converging ones, or like Stirling's that and these anti-inductive things that converge, and the non-standard and such, which do, and so they have real analytical character and are objects of mathematics, and are even particularly profound and superclassical. These are the things we're looking to understand a little bit better, while at the same time helping kind of make some apologetics is explaining. It's like, well, at the time they didn't really know all the things, the reasons why, and so we pulled together what was right about what they said, and at the same time taking some of the justifications, implicit or explicit, they might have had, and saying those weren't the right justifications. Here are some other ones that do suffice, as in our limited lens, in our limited view, that this is a sort of usual approach to dogma and doctrine, that there's dogma and doctrine, and the dogma is that dogma changes for any reason, as insofar as that then it results most principled of these things. So meters per second or seconds per meter. The other day I was standing in a slow line somewhere, and I figured it out. It's like meters per second is when you're moving at least 1 meters per second and seconds per meter is when it takes at least 1 second per meter. So that seems pretty simple. It's like whatever's in effect is whatever is more than 1, because they're reciprocal, and one's going to be greater than 1 and one's going to be less than 1. So just like frequency and wavelength or whatever, which is very large, which is very small. You know, according to our units in the dimensional analysis, and here I mean the fuller dimensional analysis, not the lesser dimensionless analysis, or the pi theorems, Buckingham pi theorems, and this and that. The principal component analysis is reduced to terms, making for a general linear model that is absent any of the conditions otherwise that result in having detached or truncated what are otherwise these implicits in terms of anything the unlinear or the infinite expressions. So fuller dimensional analysis is that 1 meter per second and 1 second per meter are about the same, but then like 0 meters per second is kind of like, well, how long is it 0 meters per second? So it's seconds per meter. So that was just something that kind of helps explain, like, well, in terms of sense, the relative sense of things, what has become the relevant, the sense of the motion or the sense of the rest. And so these are the kinds of things that as I was standing in line, it would slowly move forward until such time as I reach the front of the queue and this and that. That these are the kinds of things that have it so that it helps to reflect on why, also for matters of perspective and projective, that would be a real thing too. It works out then that it gets into whether it's easier to maintain larger numbers or smaller numbers. Now, one might have heard, it's like, well, it's always easier to keep smaller numbers because there are not so many of them. They're not so large. The idea is that the limit is like I can consider like particularly large number, and that's the end of it. And then and then among that, there's also this reciprocal inverse concern is like, I can't tell the difference between small, smaller, and smallest, except insofar as they're not large and they're small. What's to me made the difference between this microscale and macroscale? They're both just not this mesoscale. Or in terms of, as was read about the microcosm, the classical definition is the subjective man is the microcosm, and the surrounds and all of objective the reality, the macrocosm. That the atomic scale is a macrocosm too, and that whether or not it's easier to keep track of larger numbers or smaller numbers, as it's easiest just keep track of one. And then as with regards to larger numbers and smaller numbers, is with regards to whether it's easier to keep track of how long it will be to compute them, one in terms of the other, in terms of whether it's also that it results in their products, adding them up. It's like the difference between how long this was in motion and how long this was at rest makes it so that adding up for the entire time it takes to go from point A to point B, that if it's just like how many seconds was at 0 meters per second versus how many meters were accomplished per 1 second, then to figure out for 1 second and 1 meter, B minus A, and then that difference becomes easier to compute in terms of not just one system units, but two systems units. Meters per second or seconds per meter. It's meters per second and seconds per meter. Those aren't commensurate terms, but they're reciprocal in the commensurate terms. If they have all their derived terms, though, then those aren't so necessarily algebraic, arithmetic, and so on. These are the kinds of things that help to effect to relay that in terms of then algorithm and the mechanics is a simple mental model of the things, and the least necessary resources, because there's never enough. There's no free lunch, you know. How to figure out how to keep track of these things is like so. So I thought that was amusing, and it sort of amused me. Meters per second or seconds per meter. So let's take a look. We've been reading from these. These are the more ancient Greeks. Early Greek philosophy. Often it's really I've really felt educated and learned over the past years from starting to learn about all these different classicists and the philologists and the historians and in this fields of mathematics and logic and philosophy and physics, because it's kind of like the other day I felt so proud. It's like, well, I kind of have a grasp of the concepts of physics and philosophy that arises from the different schools of men, of East and West, of ancient history and modern history, and the times in between. And so I felt it was so great. And then I was reading a book, and it was from about 40 or 50 years ago, and the author was going through this same sort of enumeration of, like, talking about Anaximander and getting into Lucretius and explaining how some of the things like, well, Lucretius, thousands of years ago, already had this theory of atomism with the student Democritus, for whom we say it's Democritus in chemistry today and atomism. That again, it helped me remind me of the great thing about these, why the classics and the classical is considered paramount, and why Platonism is kind of the school of. And that also, of course, it's advised by existentialism and logical positivism, and then that we can have both the teleology and the ontology, and not so much the void lacking either. So, this author is a classicist. Says, one remarkable discovery must be singled out. The reconstitution and publication of the Strasbourg papyrus of Empedocles has added vastly to our knowledge of that curious thinker. So this is just in the second and third edition. So too, but for different reasons, have the chapters on Heraclitus and on Democritus. So Heraclitus kind of associated with dual monism and heroic faiths, and then Democritus largely with the concept of thought is like, well, the usual schools, we have finite things in one, and they're wholes and they're parts, and so there are no atoms. Democritus is like, I'll do atoms, and so it's kind of associated. Whereas Aristotle is like, he's kind of Aristotle reminds me a lot of Hegel, because both were great analytic minds, and very much so, very very deliberate, and both very very technical. And so there's the writings of Aristotle and the writings of Hegel. And so when Aristotle came up with like his prior and posterior analytics, and like, here's inference and induction, and here's deductive inference, how not to get fooled by being led along astray, and these kinds of things, it's really pretty great. And so when he gets into these notions, as we were discussing here before, at least the Aristotle's continuum is kind of like, well, we have Zeno's continuum, the Archimedean field, and Zeno's continuum, the motion as of just linear, that also kind of must be. And so when we talk to somebody like Democritus and atomism and such, then we'd associate also with Plato and substance and the wholes of things. There's still it's still a holism, and still it's a monism, but it's after infinite induction, deduction that arrives at infinite induction. Deduction arrives that it must be not just forward inference, inductive inference, but infinite induction. Numbers that gives that there is such a thing, for that the Archimedean field has infinitely many members, not just unboundedly many and potentially infinity, but an actual infinity. They sort of go together. And so then relating to these, because what's otherwise we can just start talking about these objects in mathematics is by giving names of the objects of arithmetic and algebra and number theory and geometry and topology and function theory, for examples, sets and parts and wholes and functions and relations and predicates, terms, syntax, and their semantics. It also helps to reflect on associating with schools of people, because that follows a course, the development that's kind of similar to one person's development, any given person's development of these concepts and their accumulation of them into their tool set. of these concepts and these abstract and more general concepts and these more specific, more technical concepts. So it helps to relate like this, a three-part thing of just the terms, please, poster heroes, and the person themselves, to keep these things together, to help relate them to other people, and to help relate them to them as their own things. So that's kind of how it's largely always been. Well, that's so. There's many times where it's when you have reform. A lot of times, reform's goal is to take things that have over time been overgrown. Overgrown. Excuse me. As they're overgrown, that the things that it reflects is like the maintenance of a garden and the organic. And so when something becomes root bound, that means that it's outgrown its place. And so it would need to, even if it were replanted in a newer place, it wouldn't be able to spread its roots. Or if its canopy is like so when dealing with trees, or the idea of a garden. So this reformation in theories then gets into turning over all this stuff and getting into what's abstract in general and what's sensible, fungible, and tractable, to arrive at then how to make it so that then the terms become flexible and sensible, fungible, and tractable, and accessible. So in that sense, that's where we get into the turf of the terms, and then also with regards to when things that are kind of new in their edifice and they sort of arise in the mists of the periphery of these things, and they're named like Stirling's formula or something, that later they come around kind of like simple closed connected curves, or what we call Jordan curves. Whereas after Camille Jordan's theory of simple closed connected curves, that was what it meant. And then it's just like this so now, and it's a little simpler to keep it in those terms, because at that point in time, whether the terms are disassociated with context, and whether the terms are in this a sense of their development or in the sense of their usage, has this is how it grows. The Hilbert's Infinite Living Museum of Mathematics. A terrarium, as it says. So, scholars, both modern and ancient, Barnes goes on, have supposed that there were also connections between the earliest Greek thought and the intellectual concerns of the Eastern empires. Babylonians, Asia Minor, Thales' knowledge of the eclipse, Babylonian, pre-Socratic Egyptian, pharaohs, Babylonia, Lydia, Miletus, and these kinds of things. So yeah, Greece, west of Turkey and the Dardanelles, that was, and which connects Africa and Asia and Europe, is of course a great crossroads, and always has been. The Silk Road has been around a long time. The Salt Road through the Sub-Saharan has been around for a long, long time. The world is orderly without being divinely run. Now, this is just, it's one thing to say that the world is orderly, and then another to say that it's and intelligent actors need not care at all whether or not the world is orderly. There's still the notion of free will, and so there's also that notion of responsibility that goes with it, and as well that determinism is still the course, and everything above that, while it may abstractly be a monism, because there's a term that by definition is a thing, that for all that matter, it may be a monotheism, super scientific, and that's just saying that that's just let out, and super scientific. Either way, it's super scientific. Much like either the Big Bang hypothesis or the steady state hypothesis, both do have models that are simply not falsifiable. Because there's infinity involved, so from perspective and projective, it's too far to say. In his first book of Metaphysics, Aristotle wrote a short account of the early history of Greek philosophy. He's talking about four causes, explanatory schemes. So this kind of invokes, disambiguating the universal quantifier for each, for any, for every, for all. In the language of Kleinian regular expressions, kind of for any question mark, for any star, for any plus, for any dollar, match the n. These are the kinds of questions about, like, well, are there four kinds of schemes of quantification over terms that reflect that they kind of apply at all for each, for every, or for all, that it's necessary in the syntax to make it so? That's one of those things. Then these explanatory schemes kind of hearken to the reading from Nozick and the fundamental question of metaphysics, and it's like, well, say we have infinite many terms, and they all say nothing. So how do we ever get something? And well, you say, well, you just quantify over those, and then you get an extraordinary term out of that. You can say it's a liar paradox, or you can say it's something. You can say that they're all just truths, and then we're not saying anything, and it arrives at something. Whether that's an explanatory scheme or vis-a-vis what's pragmatic, what's heuristic, what's relevant, that for relevance logic in the higher order and all such matters of practical fact, that's matters of fact. The distinction between nature and artifice, in Greek between phusis and techne. So when I say the technical philosophy, I intend that to include the metaphysical as well, but it is a technical philosophy. In the first fragment of Heraclitus, the term phusis designates not the cosmos as a whole, but rather principle within each natural part of the cosmos. Here I'd relate that to these primarily elementary fundamental theories. All one theory. When this is where foundations is a singular term. Foundations is not a plural. Foundations is the foundations. The foundation. When the pre-Socratics inquired into nature, they were not only inquiring into the natural world, they were inquiring into the natures of things. Moment in motion. See, there's perhaps a summary will guide us to something as with regards to. Here's the list of mentions of authors. And here's an index of terms. There is not really a section on moment, but there is on motion. See also change, void, eternal, impossibility of. (31), 136, 137. So on page 19, it says it introduces the notion of eternal motion. And so the eternal motion is kind of like it could be the notion of the restless universe. It's just like the prime mover. Siepo muove is what Galileo said, yet it moves. So this is out of Anaximander. And he's talking about various duals. And so he kind of basically always says, well, this way, yet also this way. This way. Or he talks about the extremes of things. He says that the earth is cylindrical in shape and is a third as deep as it is broad. Well, that's kind of a thing. Anaximander says, there's a circle. This is the sun, at the hub of the celestial wheel. As for the limitless or infinite principle or element of all things, a few words from Anaximander's books are preserved. The earlier surviving words of Western philosophy. It is uncertain and a matter of vigorous scholarly controversy exactly how extensive the citation is. Those who hold that the element is one moving and limitless, Anaximander, son of Praxeades and Legion, whose successor and pupil of Thales, said that limitless is principle and element of the things which exist. So limitless is here are these completions, or the infinite. He was the first to introduce this word principle. He says that it is neither water nor any other of the so-called elements, but some different limitless nature from which all the heavens and the worlds in them come into being. So here we might say this is a continuum of these things. The idea that there is just one continuum is, in physics, in the theory, it's called that there's a hologrammatic universe, or out of even just one dimension of a continuum, that it's also two dimensions. It's an infinitely dimensional continuum, and it's just a continuum of the things, and then all its reticulations and manifold variations make one thing. It is the thing. That's again reaches to the A, the super scientific, B, kind of exceeding definition, and C, not really associated with the otherwise the thing. But at the same time, in all sorts of different usual milieu, you can make a continuum analysis of it, and it is exactly that. That's what it is. And this is why we have, beyond just invariance, symmetries and conservation laws, quasi-invariance, symmetry-flex, and continuity laws, extensions of invariance, symmetries, conservation law. For they give justice and reparation to one another for their injustice in accordance with the ordering of time. So here this is the attenuation and dissipation and restitution and oscillation in terms of the tendencies and propensities of the sum of histories, sum of potentials, ... in time. So Anaximander is a generous reading of Anaximander through the lens of these terms. Sees kind of why they're profound. He speaks of them in this way in somewhat poetical words, yet they are. It is clear that he observed the change of the four elements in one another and resolved not to make any one of them the underlying stuff, but rather something else apart from them. So this helps effect to reflect on the notion of the mathematical objects this way. That what's primarily elementarily fundamental, or what's primary, out of these elements, the things of the things, the primeval, before they're primary, it's kind of primeval in this organic garden of these things, in a sense. That for physics, there's also a notion of four forces, or as with regards to the four fundamental things of the atomic theory, proton, neutron, electron, photon, as with regards to, well, light's not exactly electromagnetic in terms of radiation, and protons and electrons are both charged, but neutrons are not. And well, protons and neutrons are both massy, but electrons and photons are not. And otherwise, why it's kind of, in one sense, a threefold forces, in another sense, a fourfold forces. Then that for this field theory, that the four elements, earth, air, fire, water, kind of help just affect to relay this square of opposition and a square of opposition, these things, which is getting a little bit too generous for numerology, but in the same sense that technically that is the understood nature of the gauge theory, that's the field theory, that's the fundamental theory today, that is physics. It is with reason that they all make the limitless a principle. So you kind of define inversion as the first principle, because the limitless just kind of arises from that. Does inversion just go back and forth, or does it just go around and oscillate? Or does it go all the way around and make always something different? And so there's a sense that it does. And so whether the infinite should be the first axiom or the first principle, here it's said that it is with reason that they all make the limitless a principle, for it can neither exist to no purpose nor have any power except that of a principle. Well, the inverse is just kind of what is was and what was is, and that kind of thing. Any sense at all to do with passage of time. Whereas this the limitless says of the infinite variegation of things. Again, that's one of the concepts of these talks here, is that a certain least complicated infinity is a thing. It is available to reason. It is available to object sense. It just is a limitless thing, and that for either purpose, either exists to no purpose or being accessible to the senses, is that it's exactly extensible to these object sense, the thinking or reasoning senses, and that it's demonstrable by the phenomenological senses in any kind of context of time, vis-a-vis like an instance of a thing. It's not just like, I see a clock. It's like I see a clock, So this is just to say that the limitless is a principle, and not like a law or the feature of the things, is that it's at least enshrined as a principle, and that it also is the thing. Or have any power except that of a principle, for everything is either a principle or derived from a principle, but the limitless has no principle, for then it would have a limit. The idea is that, there's only these particular mathematical things that add back up, and so when we define the infinite limit and after inductive inference and infinite induction, then it goes somewhere, it gets somewhere. When it's associated in mathematics, that's courtesy the objects of mathematics. And that otherwise it's just a cases in the unbounded and not being contradicted. And so it's something to be said that so this is a little more fair to say that the limitless has a limit, is that it's not just apeiron or the unmeasurable. It adds up to what it is and how it should be. Hence, as I say, it has no principle, but itself is thought to be a principle for everything else, and to encompass everything, to steer everything, as is said by those who do not set up any other cause, for example, mind or love, apart from the limitless. And so in the theory of mind, or that of love and beauty, or these other kinds of usual notions of perception, or the semiotics, or anything to do with the way things should be, as, for example, the Sufis and their notions of love, and that being kind of like the prime mover of this these philosophies, has that here for the technical philosophy. It's both perfectly suffices and is actually necessary. And it is also the divine, for it is immortal and indestructible, as Anaximander and most of the natural scientists say. Or it's perfect. And insofar as the divine is perfect, then it is too. Belief in the existence of something limitless comes mainly from 5 considerations. From time, since this is limitless, from the division of magnitudes. Mathematicians use the limitless, again, because only in this way will generation and destruction not give out. Only if there is something limitless from which what comes in being is subtracted, again, because what is limited is always limited by something, so that there cannot be an ultimate limit if one thing must always be limited by another. Especially, most importantly, there is something which raises a puzzle for everyone alike, because they do not give out in thought. Numbers seem to be limitless, and so do mathematical magnitudes in a region outside the heavens. But the region outside is limitless, then body and worlds also seem to be limitless. For why should there be here rather than there in empty space? Hence, if mass is anywhere, it is everywhere. At the same time, if empty space and place are limitless, body too must be limitless, for with eternal things there is no difference between being possible and being actual. Aristotle. So, Aristotle says that for there to be the infinite, it's actual. So, these concepts are enduring, and we have to find them in the antique and the classical, because that's where kind of the priority is for them, and because over history, the accumulation of all the people who've known these studies all over time are the same. The same. So for seconds per meter and meters per second, and then trying to find that, and that's one of the allure, the reasons why trying to discover something of real analytical character in the unbounded in the nonlinear and the superclassical, that's not also available to some of the simpler means, for example, that Aristotle establishes for inductive inference and these kinds of things. Stuff that's classical and also as of finite means, which is the most usual way to arrive at something and be able to relay to somebody that something is so. Without having to get into an entire discourse and convince them that the infinite exists and all this kind of thing. And that, as Aristotle just said, that the actual and potential are no different. You know, that these are the kinds of things that then get into trying to find what for this moment in motion is really, it's more a matter of finding infinite expressions to make for this fractional orders of the analysis for meters per second or seconds per meter, and root meters, cube roots of meters, and over cube roots of seconds, and these kinds of things. Well, what is that supposed to mean? Well, the other day, one of the ideas from these talks is the identity dimension, and after the identity dimension came up and being all, singular in the envelope for a bunch of different things in the integral analysis, like the linear fractional equation, Clairaut and D'Alembert, it's kind of like zero is a singularity, and then there's this. Is the stop derivative is the idea is like, well, we have the usual notion that for powers and their roots, then we have like powers and the derivatives, and those also just kind of decrement powers, and then how it works is that that goes to zero, and then for negative powers, how that works is they come up and makes natural logarithm, and the various forms then that come up of incrementing or taking the inverse of that. So each of those is an increment, meaning one whole at a time, the first derivative, the second derivative, the third derivative, and this kind of thing. So this idea of the fractional derivative is a continuous analog to the derivative, and then it's with regards to operator calculus and making this continuous semi-group or something like that, which is kind of the idea of this stop derivative is to make a group above and below zero of these things. That it's similar within his methods of means of interpolation, these considerations, how to go about approaching it as like a thing. And so it's interesting that again, the fractional calculus is one of these lesser explored fields, yet saw a great amount of development, like for example, with regards to development of electromagnetic theory and a bunch of the things that came up after, like the telegrapher's equations and Heaviside and all that kind of stuff, with regards to what computed, how things go, that computes how things in hydrostatics go. And so there's much to be said for that. It's definitely got practical applicability, besides the fact that differential equations model pretty much anything in terms of time in themselves. It's the way of the things. It's all a dynamical modeling in that sense, is the dynamics of the things. So it's very exciting in a sense to try to figure out how to make some of these connections in the fields, because they don't have one already, and then it's with regards to solving some things or making something besides the whole notions of the foundations and saying, well, at least this all is true. Matter of factly, it's true. And then there's also it's like, and it's not closed to this greater truth, and then it's extraordinary and super classical and all that. It is what it is. If there's a theory at all, it has to be a theory of the thing. So that's pretty much the idea. So meters per second and seconds per meter, yeah. Moment in motion. Geometry is motion. Toodles.